apologies for the link issue, but hopefully people will mosey in as time moves along. So this morning, we have two senior forecasters, John Hitchcock from WFO Buffalo and Tom Wasula from WFO Albany, presenting on two very timely topics, two respective flooding events, one in Whitehall, New York from August of 2020 from WFO Albany, and one from September 7th of 2020, a wake depression flooding event from the Buffalo CWA. So this morning, following the calendar of the events from this period of time from a couple of years ago, we'll start with Tom's presentation on the August 4th, 2020 Whitehall flash flooding event. So Tom, you have the floor, sir.
Okay, thank you, Jordan. Let me just get my screen up here. Can everybody see a single screen now?
Yeah, looks good to me. You're good to go.
Okay, thank you, Jordan, and thank you, Jeff, and thank you everyone at Eastern Region SSD for letting me share this presentation on a very significant flash flood that impacted the Albany forecast area in late August 2020. The last time I was able to share this presentation was at the first New York State Mesonet Symposium, and it's a really intriguing case because of the impacts it had on a community and in our forecast area. So the first thing I open up with is it's debated often that what is a flash flood? Flash flooding is the definition kind of gets stretched and used in different ways, but this case is going to be one that's an exception, and one that the definition we give our skywarn spotters is a rapid and extreme flow of high water into a normally dry area or a rapid water level rise in a stream or creek less than 6 hours requires immediate action to protect life and property. And there's a slide there, an image on the left, some flooding in our forecast area in 2021. And on the right is a very high impact event we had in downtown Troy, where a round of heavy rain came in the morning, and then we had strong to severe thunderstorms in the afternoon. And it produced 1 to 3 inches of rain, and it caused sewers and basically parts of sidewalks along the blew up, basically the backup of water, and street sweepers had to come to the streets of Troy and the suburbs because of the amount of rocks and flow and the impact it has. But a flash flood warning in our forecast here, we usually issue about 22 a year from the 10-year climatology. What's interesting about 2020 is that we only issued 7, but one of them happened to be this event. And this is what I mean by it kind of jumps out at you what a flash flood is. Is it, 2 to 3 feet of standing water? Is it a foot or more of moving water? In this case, the exceptional amount of rainfall basically put cars underwater. These are cars in the Whitehall community along Route 22 underwater here. I can see a little closer view. And then the Whitehall School District with the middle school, high school complex. You see a foot or more of standing water outside the school, and the school took water in their auditorium. It tore up the gym floor. It did several $1 million worth of damage. So this is a very localized high impact event we're going to talk about. So what causes significant flash flooding in a concentrated area? I'm going to tell you, this is an anomalous, low predictability, localized high impact event. That's what motivated me, because it wasn't anticipated at basically the local level all the way up. We weren't even in a marginal excessive rainfall outlook for this day. And part of CSTAR 7, one of the aspects that we're looking at is severe weather, including flash flooding in complex terrain, improving tornado warning guidance, using new advances with dual pole radar data, and applying New York State Mesonet data, which I'll show some throughout this presentation. So an outline for the talk, I'm briefly going to touch upon the geography and history of Whitehall, explain where it is and the history behind it, a synoptic overview, review some SPC RAP and New York State Mesonet mesoanalysis data, flash flood guidance and the PWAT analysis for this day, a brief radar analysis, and then I'm going to look at a few images applying magnitude and impacts from FLASH, which FLASH is for the flash flood. FLASH stands for, again, flood locations and simulated hydrographs. I tend to remember as FLASH and forget what the acronym is, but that's what the acronym is defining, flood locations and simulated hydrographs. So first, our forecast here, because I know we have people from different parts of the region and across the country on, is we cover 19 counties in Eastern New York and West New England, 15 in New York, 2 in Southern Vermont, 1 in Massachusetts, and 1 in Connecticut. And a third of our forecast area is in complex terrain above 1,500 feet. And there's the outline of our forecast area. We're going to be focused on Whitehall is in this northernmost area of Washington County. And basically you have the Adirondack Mountains here, Lake George, the upper Hudson River Valley connects, and then the lower reaches of the Champlain Valley. But basically we see at times, we're going to see from this presentation, the role the terrain to the northwest has for the convection that forms and impacts this area. Whitehall itself is, again, near the northern, not quite the northern tip, but near the northernmost portion of the county. It's a town, a very small town. You can see Route 22 that runs north-south from New York, and then it moves into Vermont to the northwest here. This is Lake George to the west. And this community is not a very populated area. It's a community of roughly just under 5,000 people. The 2020 census, 3,926 people are counted with the census in the village. It's considered or nicknamed the smallest town in New York. And some history back to the Revolutionary War is it was called Skenesborough in 1759 when it was settled by land from a British officer named Philip Skeeny, who was sent back to England after the Revolution as he was declared an enemy of the state due to land dealings. The town was captured by American forces with the Benedict Arnold Philip Schuyler Navy. And after the war, the town's name was changed to Whitehall. So this was in the late 1700s. And in 1960, the New York legislature declared the town the birthplace of the U.S. Navy. And driving through, going to Vermont at times and in that area, there is a sign there, and it is the birthplace of the U.S. Navy according to the history and basically the New York State legislator in 1960. So this small community is going to be impacted by the flash flood. At 12 UTC at 500 millibars or 500 hectopascals, there was a positively tilted upstream shortwave trough moving through the Ohio Valley and the Great Lakes region towards New York State. Not very cold off, -10 seal off, and this isn't an exceptionally strong trough. But we did have a shortwave trough approaching, and basically synoptic forcing not exceptionally strong, but again, a shortwave trough approaching the area. The 1,300 and 1630 UTC day 1 and day 2 outlooks from SPC had a marginal risk across most of our forecast area, most of West Central New England, and into like the Pennsylvania, New Jersey, and the upper Mid-Atlantic region. So there was the marginal risk for a few isolated or a few severe thunderstorms this day. And again, I already mentioned that we weren't outlooked at all. And again, our anticipation was not for flash flooding this day. It was more on the lookout for some isolated strong to severe thunderstorms. The reason why, again, is that the soils were not very saturated and the flash flood guidance was relatively high. In the Whitehall area, the 1 hour was 1.4 to 1.8 inches in 1 hour. The 3 hour was 1.8 to 2.5 inches for 3 hours. And even the 6 hour was also in the 2 to 3 inch range. Again, it was a little bit lower compared to other parts of the area, but overall, again, it was not, we weren't sitting on wet antecedent conditions before this happened. 20 UTC, an hour or so before the convection, 30 minutes to an hour before the convection fires, the 0 to 6 kilometer effective bulk shear from the SPC Mesonet analysis wasn't exceptionally strong. The strongest effective bulk shear was 30 knots across northern New York into northern New England, 25 knots near the Catskills. So we're looking at probably on the order of 20 to 25 knots for the impact area, maybe slightly higher. So we were anticipating multi-cell type structures, but the surface-based capes were in the 2,000 to spotty 3,000 joules per kilogram range. So a lot of instability, and I would call it low to maybe low-end moderate shear was expected ahead of this. Precipitable water analysis, anywhere in the dark shaded green is greater than 1.5 inches, but generally 1.4 to 1.5. Which is a little bit above normal once we look at the climate in a few slides here. But the one thing that jumped out was one thing in the flash flood coursing at RAC is they talk about the upwind propagation vectors. From the west-northwest, they were about 10 knots, so not exceptionally strong. So that can be a flag with above normal peak values, which Steve's were once we look at the climate. And sure enough, at 2030 UTC, just downwind of the Adirondack Mountains and over the northern reaches of the Lake George area, convection started to fire. Ahead of that, a shortwave trough, and we'll see a surface trough to the north. And temperatures that day rose into the mid and even upper 80s. There's even a few spot 90-degree readings in the New York State Mesonet. Dew point values rose to about 69, so then to the upper 60s, around 20 Celsius. So it was a very humid air mass, and with the high dew points and with the heating and the instability amounts did increase in excess of 2,000 to close to 3,000 joules per kilogram. At the surface, again, we talk about this a lot in our office. I know in other offices too. The synoptic forcing was not exceptionally strong, but there's a hint that you can see a little trough surface waves over southern Quebec analyzed by WPC with the wind flow, with southwest flow and southerly flow coming up the valley. So there's indications of like a weak surface trough here and convergence toward the moving northward of the Hudson River Valley to the upper reaches towards the Champlain area. And then we look at the Mesonet, looking at the New York State mesoanalysis. This surface convergence divergence chart comes out every 15 minutes or half past the hour. We were usually looking at it, and it did show basically at 2130 UTC, this area of enhanced convergence, negative values. So the more negative the value is basically strong surface convergence. Positive values are situated with surface divergence. So again, along or just near the Whitehall area, it shows this enhanced area of surface convergence. And the 0Z sounding is much more represented in the 12Z I'll show here from Albany. At 0Z, and this is, again, the convection is underway at this point. Surface-based CAD values are a little over 1,500 joules per kilogram. I didn't put the mixed layer, it was just over 1,100. Again, the 0 to 6 kilometer bulk shear around 30 knots. The decape values were close to 1,000. The forecast lifted indice was -4, and the reason I put that on there is in a week from now, when Brennan, the master's C-star student that finished his work, is going to talk about some predictors with back building convection next week. And forecast lifted indice was one of them that came out as a strong predictor. The warm cloud depth was around 8,500 feet, so not quite to the 10,000 in some of the training, but again, close. And the precipitable water value increased from 1.39 inches on the 12Z sounding at Albany to 1.49 inches, and we'll see where this stacks up in terms of the PWA climatology. The theta index increased to 22, which is high, and the freezing level was 13,000, roughly 13,000 feet. Again, low-level veering in the boundary layer up to just under 850 to 700 millibars, and then pretty unidirectional flow. So anything that form would likely form into a line, and that there is a possibility of a training based on some of the other mesoscale data. So the PWAT value, the 1.49 inches for August 25th for Albany, when I plotted it with the SPC PWAT climatology, it was between basically the 75th and the 90th moving average. So it was above normal, not a record, but above normal, and notable that it was above the median value and above the mean value. So basically this is an anomalous day in terms of the PWAP value. And then here's a radar loop of the event, and then I'll break it down from the radar analysis of the data. Basically, you can see multiple waves of convection fire along. The Adirondacks will be here to the west-northwest, and then kind of it continues to back build and train in time. And there's at least 3 waves. You can see the flash flood polygons come here from the Albany office and the Burlington office downstream of Whitehall. And this poor town got hit by repeatable waves here. I break it down to about 3 distinct waves, but there's 3 surges, and we'll walk through them in the analysis coming up. But you can see the first wave slams, and there's some of the wind reports come in. I show then the flash flooding as you get the second wave, and then one final third wave toward the end. So at 2034 UTC, this is about 34 minutes after the first severe thunderstorm warning, and a cross section through the core of the severe thunderstorm showed basically 50 dBz, the 50 dBz reflectivity height to almost 40,000 feet. And the minus 20 C height was about 24,000. This was 16,000 feet above the minus 20 C height on the 0Z sounding. The 60 dBz reflectivity core was over 25,000 feet, which we were anticipating it to be hail, and remarkably, we didn't get any hail reports. There could have been some, but this is a lot of precip loading into the thunderstorm. We did get a lot of thunderstorm wind damage from this initial surge. And again, there may have been some hail, but we didn't get any severe hail reports. But if that hail all melted out, it likely produced extremely strong microburst type damage, which we got with the reports. Looking at 2112 UTC, doing a cross section to the KDP, we saw an impressive KDP core that rose and then descended. So this KDP value of over 4, on the order of 4 to 5 degrees per kilometer, indicates lots of liquid water content. There could have been some mixed hydrometeors in there with hail and melting hail coming down too. Reached above the freezing level of 13,000 feet. And some research recently published by Brian Frugas showed that these descending KDP columns are something to monitor and watch for wet microbursts, and it was used for the warning decision forecasters with this event. At 2203 UTC, again, the flash flood warnings we issued at 2206, and then the concern was this area had possibly a couple inches of rain. There were flood advisories out, but then you had, again, if I label these as 1, 2, 3, you had multiple waves upstream back building and training moving towards the Whitehall area. Looking again, this is about an hour later from the earlier plot of the surface convergence divergence. It did show the maxima move to the southwest of Whitehall and an increase. So this is maybe a sign of the let up. And again, this is approximately plotted based on the mesoanalysis data. You see a little bit of a surface pressure rise. So monitoring that, the 2230 UTC severe weather summary from the Mesonet data. This is a 3-hour summary. You can see the MRMS lightning data, where the training convection occurred. The maximum gusts recorded at the Mesonet site was 29 miles per hour, which is interesting because the Mesonet site was kind of on the south end of all the action in the severe weather. The co-op site, which I'll show in a little bit, was on the north side underneath all this, which is it's near Lock 12 on the lower reaches of the Champlain locks in Whitehall. So basically, quite a gradient in rainfall we're going to see with this. So at 2244 UTC, flash flood warnings are continuing. This is when the third round of strong to severe convections moving the backfilling trains occurred, and the train cells are producing flash flooding reports were coming in. And basically, I was really impressed by this. This is a cross section through the KDP data, the specific differential phase data, and the freezing level again around 13,000 feet. That we saw the values off the chart. The values go up to 7 degrees per kilometer, and we were hitting into values of 8+ coming down. So this is tremendously heavy rainfall, possibly some strong wind still. And the ZDR values I didn't show in this slide, they were between 3 and 5, which again, some of the rack flash flood work is noted between 2 and 5 dBs stacked, that it could be very, very heavy rainfall. And we for sure were getting that once we look at the data. And the flood location simulated hydrographs. On the left image, I have the crest, the couple routing and excessive storage, max unit streamfall. And this is over the last 3 hours. So this would be from 2030 UTC to 2330 UTC. And you see values greater than 10. This would be at the edge of the purple going into the navy blue. And basically, you even see some greens here. This would indicate, in urban areas, this would be, it's a small town, but for urban areas, this would be kind of off the charts. So very, very heavy rainfall with some flooding indicated. And then the hydrophobic is like the worst case scenario. Widespread areas over 10, well into the greens here. No infiltration into the soils at this point once we see the amounts of rainfall, which again, we're uncanny once we get to that. And then here is the storm total accumulation image from the dual pole data. And the storm total actually showed 3.5 to 6.6 inches of heavy rain. And actually that was not far off. The north side of Whitehall, the north side along to the north, 5 to 6.6 inches. The radar showed, and we did have ground truth that produced that kind of rainfall. The MRMS QPE data indicated 4 to 6+ inches of rainfall. And the cooperative observer, which is along on the lock, had 5.85 inches of rainfall for the day. And I do have new information from the 15-minute data from that cooperative observer through our senior service hydrologist, Britt Westergaard, and our observation program leader, Deanna. Deanna was able to break down the 15-minute data, and it looked like in about 3 hours, breaking down the 15-minute data, the 5.53 inches of rain fell at the co-op site. Now, how much rain fell at the Mesonet site? Well, these sites, I should have gotten the exact distance, but I'm going to say roughly 5 miles. Again, not for sure the exact distance, but roughly 5 miles or so apart. 0.3 of an inch for the day. Chestertown to the northwest, coming off the Adirondacks, there are 1.1 inches. So tremendous gradient of rainfall between the Whitehall Mesonet site and the co-op site. And this is a breakdown of the meteogram for the co-op site. And basically, the temperature and it got into the basically almost to the up mid and upper 80s this day. The wind data, they show the peak wind gusts on the side, the gust of 29 miles per hour is this dot here. You can also see the drop off in pressure. And the precip data is also basically the 3/10, there it is for the day from the rain. So again, this is kind of a miss for the co-op site, but a big hit, or I'm sorry, a miss for the New York State Mesonet site and a big hit for the co-op site. And then here's the breakdown of the rainfall for the month, which I thought was interesting for the Whitehall co-op site. The rainfall on the 4th and 5th was from Tropical Storm Isaias, basically 3.56 inches of rainfall. And between the 6th and the 24th, I talked about how the antecedent soil conditions were not very wet. 1.64 inches of rain fell. And then here on the 25th, there's the 5.85 inches. So we had a wet event at the beginning of the month, and the conditions were very dry ahead of that tropical storm early in the month. And then kind of a drop off, and then the big hit here on towards the end of the month to the 25th, 24th to 25th. And then basically for the month, they had over a foot of rain at the Whitehall at the co-op site, which is very, very exceptionally high, probably close to a record. And then the Whitehall Lock C12 was the location. And then looking a few more slides here at the 2330 UTC FLASH analysis, the 3-hour QP to flash flood guidance ratio was 3 to 5 times greater than the FFG between the 2030 UTC and 2330 UTC, and basically plotting the 3-hour QP for an average return interval integrates a 200+ year excessive rainfall event or flash flood, all the purple, so pretty widespread area. And finally, again, this to show how this stacked up using the Northeast Regional Climate Center's extreme precipitation tables and analysis for extreme precipitation events. The 5.53 inches of rain fell in 3 hours based on 50-minute data from 21Z to 0 UTC at the Whitehall Co-op. And again, thanks again to our OPL, Deanna, and Senior Service Hydrologist Britt for helping me access the 50-minute data. And again, 5.5 inches, if you take something like that, it's right here on the 500-year heavy precipitation event or anecdotally flash flood. So 5.59 inches is the threat. And then in terms of the Whitehall area being hit so very hard, 5 flash flood events recorded, 10+ wind damage events. And the deputy director from Whitehall, the initial estimate was just over $16 million for the school damage, but 8 roadways closed, 21 flooded structures, 33 reports of trees, wires, and wind damage around the town. This town was hit exceptionally hard. So this was a sinkhole, one vehicle off the road from rain, even a brush fire from probably the lightning. So in summary, this is a low predictability and localized high impact flash flood severe event with 11 wind damage reports and 4 flash flood reports. There could have been even more. Weak to moderate shear environment with generally less than 30 knots, but moderate to extreme instability in the pre-convective environment. The New York State Mesonet data did show a region of enhanced low-level convergence and a sharp difference in rainfall compared to the Whitehall co-op site. Precipitate waterable values were above normal in that 75 to 90th percentile of the climate for the day, and the flash flood guidance values tripled based on the flash data. KDP columns were useful for flash flood and severe analysis, and the radar showed strong evidence of backfilling training cells that played a critical role in the flash flooding for Whitehall. Again, 5.53 inches of rain in 3 hours indicated a 500-year heavy rain event, and the 5.85 was the total for the day. And this heavy rain event is based on the analysis from the Northeast Regional Climate Center Extreme Precipitation Analysis. That concludes my presentation, and thank you for your time today.
All right, Tom, thank you so much. That was a really great presentation. In the interest of time, I guess we'll switch things over to John Hitchcock, and then right after his presentation, then we can have an open discussion and have a question for him on both presentations. If that sounds okay.
Sounds good to me.
Okay. So with that, I'm going to hand the floor over to you, John, to present your discussion on the September 7th, 2020 Wake Depression event. The floor is yours, sir.
All right, let me just share my screen here. All right, can everybody see my title slide here?
All good here. Can see it from my end.
Okay, I'm going to talk about a pretty interesting event that happened just a few weeks after the event that Tom talked about. Excellent presentation, by the way, Tom. So this is September 7th, 2020 wake depression that hit western New York. And this is actually a wind event, not a flood event, but a pretty interesting event nonetheless. So here's a radar loop of this day. We'll start by looking at this, and I'll play this a few times for you. But when you look at this radar loop at first glance, you're probably wondering why this was an interesting event. We just had a area of decaying stratiform rain moving through western New York pretty early in the morning, a couple hours centered on 12Z that morning. So I'll play this one more time. And what this is a decaying area of stratiform rain from an upstream MCS, which occurred overnight. If you look real close, maybe I'll play it once more, you can maybe pick out a few weak MCVs as the stratiform rain is weakening away. You can see a few circulations. There's one kind of crossing the Rochester area, just south of Lake Ontario, and perhaps a few in the southern tier as well, but really nothing really eye-catching in the radar imagery. So let's take a little deeper look into what's going on in this event. First, here's the local storm reports from this event. So all wind damage reports and 160 mile per hour measured gust on the ASOS of the Rochester airport. Quite a few trees and power lines down. The most significant damage was in the village of Olean, which is in the southern tier, a little bit north of the New York-Pennsylvania line. There were several trees down on homes in that village. So they had quite a bit of damage there. And some of the peak wind gust reports, these are all from ASOSs or AWOSs. So Rochester had the highest gust of 60 miles per hour and quite a few gusts between 45 and 50 miles per hour. There were several Mesonet sites as well that had 55 to 60 mile per hour gusts on this morning. So let's take a little deeper look into what's going on here, because just looking at the radar, you wouldn't expect wind gusts of that magnitude with a weakened area of stratiform rain moving through the area. So here's the surface analysis for 12Z this morning, and this is just about the time when the wind damage was happening. Most of the wind damage was within an hour or two of 12Z. So you can see a fairly deep low for early September up near James Bay, but a long ways away from western New York. So you might expect some synoptic winds with that 983 millibar low up in Ontario, but certainly not in western New York. We're still in the warm sector ahead of the cold front, which is back in lower Michigan. So nothing really synoptically that would make you believe strong winds would occur. And jump at the 15Z, this is towards the end of the wind event. Again, that cold front is still well upstream near the eastern shores of Lake Huron, and won't move through the area until very late in the day or that evening. And again, pretty strong low up near James Bay. If we go upstairs to jet stream level, 250 millibars at 12Z, there's a fairly strong jet over the northern plains along the U.S.-Canadian border, but again, well west of the area. So most of the synoptic forcing is still displaced well upstream of western New York. At 500 millibars, you get the idea. Pretty good shortwave trough, embedded within the longwave trough, but still over the western Great Lakes, over Lake Superior and Lake Michigan at 12Z that morning. At 850 millibars, again, the 850 trough is still well upstream. You can see a pretty decent area of moisture being advected north into the eastern Great Lakes, just ahead of that 850 millibar trough. But you get the idea. The strongest forcing is still well upstream in the central and western Great Lakes. Here's a look at the 12Z Buffalo Sounding. This would have been just ahead of that stratiform rain area that moved into western New York. So this balloon was launched probably just a minute or two after 11Z in the morning. And you can see in the thermal profile, pretty stable near the surface. Below 900 millibars, we still have a nocturnal inversion in place. Above that inversion, there's a reasonably unstable layer from right about 900 millibars up to just above 700 millibars. Somewhat dry in that unstable layer as well. If we look at the wind fields, pretty good amount of flow this morning, about 40 knots just off the deck, increasing to 50 knots at 700 millibars. So there is some wind upstairs available to be mixed down. Instability, as you would guess, at 12Z on a September morning were pretty stable, right just after sunrise. If we jump ahead to 15Z towards the end of this event, again, in Western New York, we're still completely stable to a surface-based parcel anyway. There is a narrow axis of weak instability developing upstream that would be behind the decaying area of rain and just ahead of the cold front that's moving through lower Michigan. But again, well upstream and not related to the wind event we're talking about here. 0 to 6 kilometer bulk shear at 12Z in the morning. Pretty strong shear upstream near that cold front, about 60 knots of deep layer shear. A little bit weaker here in Western New York, between 40 and 50 knots of deep layer shear. Jump into 15Z, very similar values. The strongest shear is upstream still, but a decent amount of shear moving into Western New York. Looking at 0 to 1 kilometer bulk shear in the lowest levels of the column, we do have a fairly strong level wind profile, as you saw in the 12Z Buffalo Sounding. So we have about 45 knots of 0 to 1 kilometer bulk shear available at 12Z and very similar values at 15Z through the course of this event. Lapse rates, low-level lapse rates, as you might guess, at 12Z, first thing in the morning, pretty weak. And as we jump ahead to 15Z, they start to increase some, but mainly over eastern New York. Remember, we have that area of decaying stratiform rain and dense cloud cover moving through western New York. So not a lot of heating. So really the point of getting across is both synoptically and from a traditional convective standpoint, we would not expect strong convectively forced wind gusts or synoptic wind gusts in western New York on this morning. So let's talk a little bit more about a wake depression, what these are. Now, we all know that most MCSs, or almost all MCSs, have a mesohigh within the stratiform rain area that forms from evaporative cooling of that stratiform rain. But in some cases, we get a wake depression that forms behind the mesohigh, typically located near the trailing edge of stratiform rain. And if that happens, there's a pretty strong mesoscale pressure gradient that develops between the mesohigh and the wake depression. And then you get a strong mesoscale ageostrophic wind component that goes from the mesohigh to the wake depression. And that can cause a brief period of strong winds in an area and a time you might not expect it in an MCS event. And some of you may have heard of this idea of a heat burst. These happen rarely, especially in the Midwest and the plains. And this is how that happens. They're associated with wake depressions. I actually experienced one in Kansas one year playing golf, which was interesting. So here's a schematic of a wake depression. This is from a paper by Johnson and Hamilton back in 1988. So you see the mesohigh in the stratiform rain area behind the squall line. You'll often have a weak pre-squall line mesolow right on the leading edge of the squall line. But in some cases, we get a wake low or wake depression near the back edge of the trailing stratiform rain area. Now, a few ideas on what causes a wake depression that I found in the literature. That same paper by Johnson and Hamilton in '88 proposed that wake depressions form from subsidence near the trailing edge of stratiform rain, where evaporative cooling was not sufficient to offset the adiabatic warming from the subsidence. Numerical study by Gallus in '96 modeled that when precipitation rates decrease in time with an MCS, so when the precip area is weakening, and if you think back to the radar loop from this event, that's definitely the case. The rainfall is decreasing in intensity and area in this case. And when that happens, you get strong subsidence and a wake depression may develop. Another paper by Lance Bossart and others in '88. So an Albany connection there for you, Tom, proposed that strong subsidence in the rear of convective lines may produce gravity waves, and gravity waves might play a role in forming the wake depression. All right, these next series of slides, they're going to be a still frame of radar at the time of the strongest gusts for various locations. And then the large red arrow is going to be the direction of the peak gust. So we'll take a look at this one. This is for Niagara Falls, which is marked by the dot there, right near the northern edge of stratiform rain. Niagara Falls at a peak gust of 51 miles per hour out of the south. So a few things of note here as we look through these. One, The location where the strongest winds are, it's going to be near the trailing edge of stratiform rain. So if you think about traditionally where you think the strong winds are going to be in an MCS or a squall line, this is the exact opposite. And the wind direction is often unexpected as well, because think back, we're dealing with the mesoscale ageostrophic wind that's going from the meso-high, which is kind of embedded in the middle of stratiform rain, to the wake depression, which is located on the back edge of stratiform rain. So in this case, we have a south wind at Niagara Falls, 51 miles per hour. On the next slide here, peak gust at Buffalo of 49 miles per hour out of the south-southeast. So again, a pretty unexpected wind direction for that peak gust near the trailing edge of stratiform rain. Jumping ahead a little further to Dansville, and at this point, you can really see how much the stratiform rain is decayed at this point as this MCS, a remnant MCS, is weakening. And again, right at the back edge of trailing stratiform rain, it's probably not even raining at this point in Dansville, and they have a 51 mile per hour gust out of the south. Okay, this next series of slides, these are screenshots of meteograms I grabbed from this event from the New York Mesonet. So in the meteogram on the top, in the reddish shading, that's 2 meter temperature. In the green shading, that's surface dew point. The middle is sustained winds in the dark blue, wind gust in light blue, and then wind direction are the data points that are plotted in the middle. And then down on the bottom is station pressure. So not sea level pressure, but station pressure. So here's the meteogram for Buffalo, and I've kind of marked the timing of the wake depression and also the meso-high. So if you direct your attention to the middle, you can see peak wind gusts there coinciding precisely with the passage of the wake depression, which comes after the meso-high. If we look at Batavia a little further east, that's halfway between Buffalo and Rochester. Similar idea, so co-located or co-timed with the peak wind gust, in this case of about 50 miles per hour at Batavia, we see the passage of the meso-high and then the wake depression. Also of note, if you look up at the top, look at the temperature trace for Batavia, you can see a nice little temperature rise at the same time we get these wind gusts, same time we have the wake depression. Now, because of the time of day, it's a little hard to tell, is this just diurnal warming in the morning, or is this actually a little minor heat burst? But I would argue we did have a minor heat burst with this event. You can see a pretty good rise in Batavia. And then just after the passage of the wake depression, the temperature actually comes back down a couple degrees. So it does appear there was a very, very minor, almost imperceptible heat burst with this event. And we see something similar at Delavan. This is down to the southern tier. So this is kind of near the peak of the wind speeds and the wind damage that we got in the southern tier. You can see peak gust here at 60 miles per hour in the middle row. And up at the top again, you see that suggestion of maybe a very minor heat burst with a rise in temperature, then a fall of a degree or two after the wake depression passes. And down at Olean, this is close to where some of the best damage was in this location. At the Mesonet, they had a peak gust of 50 miles per hour or so, and you can see a pretty strong mesoscale pressure rise fall couplet in this case. I know the numbers are small, but the pressure goes from roughly 964 down to 955. So you get an almost 10 millibar in 2 hours pressure rise fall couplet. It's a pretty significant pressure gradient as this combination of meso-high and wake depression go through. Now, the Mesonet over in Central Square, which is in Oswego County, this is away from the passage of the decaying MCS. So I just want to get across the point that, there wasn't any type of synoptic scale pressure rise fall couple moving through. Just have a relatively steady, gradual drop in pressure with the approach of that low pressure system up near James Bay. No real strong wind gusts here at this site. So you kind of get the idea that what we were seeing in Western New York was driven by a convective process from the decaying MCS. So if you watch out situations for wake depressions, if you have an MCS that's weakening and moving downstream, kind of racing out ahead of the stronger forcing instability, getting out ahead of the low-level jet that's supporting it, and if you have a rapidly collapsing area of stratiform rain associated with the decaying MCS, that's a situation based on the research and based on the events that I've seen where you may see strong wind gusts from a wake depression. Now, once you've recognized that wake depression is possible, what warning do you issue? In most cases, these are going to produce sub-warning criteria winds and no damage. But in the rare cases like this one, where you're getting strong enough winds to produce damage, what do you do? Severe thunderstorm warning, a high wind warning, special weather statement. So if you're getting sub-severe winds, special weather statement is obviously the best choice. But if you're getting winds strong enough to produce damage, really none of our warning products fit this very well. If you go with a severe thunderstorm warning, the time duration fits. The winds typically last for perhaps 15 or 20 minutes from these. It doesn't really fit the meteorology, though. It's hard to explain to all of our users and customers as to why you're issuing a severe thunderstorm warning at the trailing edge of a relatively benign-looking stratiform rain area. On the other hand, a high wind warning, maybe it fits the meteorology a little better, not really. Definitely doesn't fit the time duration, because high wind warnings are supposed to be longer lasting events, and these last for, like I said, 15 or 20 minutes typically. And they're very difficult to issue quickly in GFE. I mean, ideally, you'd want to have wind grids that supported the high wind warning, and you go through the whole process of creating a high wind warning grid and issuing that. If you did all that in GFE, the event would be over before you could even get the warning out. So there's really no good answer. We had a discussion. I presented this at our spring workshop last year in Buffalo, and we kind of came to the conclusion that if this ever happens again, I think convective warnings are probably the best option, a severe thunderstorm warning. But if you do that, you're going to have to explain to your partners what you're doing on NWS chat, at least to the media, so they can kind of try to explain it to the public as to why there's a severe thunderstorm warning and damaging winds in a spot we typically wouldn't expect. So a few challenges. They really can't be forecasted with any reliability in advance. Extremely difficult to anticipate these until they begin to happen. But again, the thing to watch out for is that rapidly decaying area of stratiform rain as an MCS is weakening, moving into your area. And no weather service product really effectively fits these rare events. They're difficult to handle in terms of messaging to the public and partners. But again, I kind of think a severe thunderstorm warning is probably the best option if you ever face one of these situations. And by the way, this wasn't our first wake depression. We had one on June 7th, 2011 in Western New York. This one wasn't quite as strong, peak gusts of almost 50 miles per hour at Buffalo. This radar image was from about the time of peak gusts at both Dunkirk and Buffalo, and the peak gusts were out of the south and southeast. Again, you get the idea of the strong ageostrophic wind component going from the meso high to the wake depression. All right, that's all I have for my presentation. I'll open it up to any questions for either Tom or myself now.
All right, John and Tom, thank you so much for these great presentations with a lot of really great information, both from a conceptual model and general forecasting standpoint. I guess I'll get it started with a comment/question to both of you. So on the slides towards the beginning of both of your presentations, you noted the environment, you noted, the synoptic setup and all that, and that kind of falls into the category of mesoanalysis, right? Getting your mindset for the forecast and getting an understanding of what the environment's going to look like. So I guess my question is, how did that mesoanalysis play a role through each of the events, and how would you say that influenced some of the warning decisions that ensued for each event?
Go ahead, Tom.
Okay, sure. Mesoanalysis was critically important. I think that's something we have done, but we do it even more. I think that a lot of forecasters use the SPC RAP analysis well, but I think we've really incorporated a lot more looking at the New York State Mesonet in particular, and the real-time images and plots we get. Not only the rainfall amounts they're super helpful too, but the instant every 5 minutes getting the wind gusts, and also the certain graphics that come out 5 to 15 minutes, like that surface convergence and divergence, which helps to reinforce what you're seeing on the radar and what to anticipate. So I think we definitely try to staff for that, and we use as much information as we can. It's a great help. Like, this is a situation that was in the afternoon, but I've mentioned this before, that even at nighttime, you're wondering, like a heavy rain event or a severe/heavy rain event, what kind of winds and what kind of rain. We had the network with ASOSs, but with the Mesonet, we can see things quicker and faster. So a tremendous help, and it's been a great benefit.
Yeah, I second that. Really, in any type of convective scenario, whether it be severe weather, flash flooding, mesoscale analysis is really critical. And in this case, New York Mesonet data it's really good data that we have in a pretty dense network in New York State. So yeah, it's critical in any convective situation.
Thank you. Mike, I'm gonna go in order. I see you have your hand raised. Go ahead.
Yeah, hi, really good presentation from both of you guys. Just a question for John. I'm wondering, did the HER or any of the cams give any indication on this event, or was it just at a scale that really the cams were even not enough?
Yeah, I didn't look back at the cams guidance, but I kind of doubt they were. You know, these are pretty difficult events for a model to capture, even a high resolution cams model. Perhaps someday when we get to real-time warn-on forecast models, like some of the experiments that are going on now, perhaps they could capture it. But really, you're just, when you see an event like this, you're really just reacting to what you're starting to see in the observational data.
Yeah, because I guess as a follow-up, I mean, how often do you see, sort of decaying MCS going across Canada into Western New York? The back edge of the precip is kind of diminishing pretty quickly. I mean, it just seems like it wouldn't be that unusual, right? But you can't be issuing warnings in advance. It's almost like you are. It seems like you're responding in real time once you get reports. There's not much more you can do.
Yeah, I mean, like you said, decaying MCSs are fairly common here, but to get winds strong enough to do damage is exceptionally rare. So, I suspect when you have a decaying MCS, there's probably a very minor wake depression going on a lot of times that's producing almost imperceptible wind gusts, but to get them this strong is rare. I started my weather service career in Indiana, and in 4 years, I saw 2 of these that were strong enough to produce wind damage there. So they do happen somewhat more often in the Midwest and the plains, but it's not even a common thing out there.
I'll also just jump in and add, and Jeff, I see your hand up just for a moment here. I'll add that the onset of the Mesonet stations and the increase in the observing platforms is what's the breaking point between observing and not observing these borderline events, especially when they're borderline severe and you're trying to establish that criteria. So the more you can get the observational platforms in place, obviously that's a critical part of this as well, along with the meso analysis too. Jeff.
Yeah, great presentation, both of you. I'd before I get to my question, maybe a quick comment related to Mike's. I think cams that actually assimilate radar data, like the HER and like the WAF system, are probably the best bet, and maybe WAFs, and especially these that have very rapid update cycles. Would seem like it would almost be a requirement to at least have a chance to pick these up in real time as they're at least as they're initiating. My question is, you both showed some really nice applications of the Mesonet data. I was wondering if either one of you had any thoughts or whether there was use of the Mesonet profiler data, and how that may have helped the situations.
Go ahead, Tom. You want to go first?
Sure, and great presentation, John, too. I wanted to let you know.
Thank you.
Yes, I did not with this event to answer your question. It's something I probably should and could look at. There are a couple of other events that we do have near Albany that I've tried looking at some of it. And some of the information I found useful, but I'm still trying to learn how to use the data more. So it's definitely something I can look at, Jeff, and thanks for making that point.
Yeah, same thing here. I didn't look at this event, especially considering I had a 12Z sounding a very opportune time for this event, just ahead of the stratiform rain. I've looked at it in real time a few times now. They're somewhat newer compared to the overall New York Mesonet, but yeah, the data looks promising that's coming out of them. I wonder, Jeff, if the WASP folks would be willing to run a retrospective on this event. I wonder if they could do that.
It's possible. Certainly can't hurt to ask. I know they're kind of making a, I think they've got an ever-growing list of, of those sorts of requests, and that, and prioritizing that with the compute time they have. But certainly a wake low, and and like you say, a wake low in a geographic area that's maybe a little more atypical might be interesting. Probably the other question is, can they, do they have the data that they would need to initialize the runs?
Yeah.
All right, thanks, Jeff. A really good point there with the vertical profiling opportunities. Tim, I see you have your hand up. Go ahead.
Excellent presentations by both Tom and John. I have a question for both of you. I'll start with Tom. I noticed in your slides that you mentioned KDP cores were helpful for flash flooding. Could you elaborate on that? I'm familiar with the research related to KDP core depth and microburst, but not as familiar with applications for flash flooding. So I'd appreciate it if you could elaborate on that.
Yeah, so we use the KDP cores to help with wet microburst analysis in the cross section, but also I was correlating basically the core depth and the amount of high values, that if we're not getting, the hydrometeors are melting out, that there's a lot of liquid water content and what's coming down. In this case, with the training, with the high KDP values, we felt that there was a lot of liquid water content in terms of them being exceptionally high, but it wasn't just near the ground and like a 2D panel, it was more the depth. So I guess we're using a twofold there for the wind, but also just the amount of liquid water content, correlating it with those high values, that there is a lot of water in the actual amounts. So maybe it's more anecdotally, Tim, but again, I think some of the rack flash flood course talked about that with the high KDP values too.
Okay, that's kind of where my thought process was going. Do you happen to know if there's any, I guess, more thorough research on that, or is it mainly just anecdotal?
Honestly, I would say probably anecdotal at this point. So yeah, that's my, I would say for that, yeah.
Excellent. Thank you for that clarification and elaboration. John, I really enjoyed your talk. It's very fitting. We've dealt with several of these wake low / heat burst / anvil induced high wind events recently, and it certainly has posed a challenge in terms of how do we message this through our products. In our area, and I should clarify, I'm down in South Texas, but in our area, we've noted that several of these events tend to last more on the 1 to 2 hour range. So that makes it a little more difficult to message through, say, a severe thunderstorm warning. So I was curious, I looked through some of the research that you highlighted as well, but are you aware of any climatology or information out there about how long these events typically last? Because I noted that your durations seem to be shorter than the ones we experienced down here. So I was curious if that was maybe, due to a difference in mesoscale environments, or just happened to be how it was sampled by the Mesonet.
Yeah, there's not, as you are probably aware, there's not a lot of literature on these, and most of the papers I found are pretty old at this point, still useful, but the research was done a long time ago. I'm not familiar with any climatology of them. Yeah, they do tend to be more brief up here. MCSs tend to move faster at our northern latitudes than down there in Texas. That probably has something to do with it. Just the general forward propagation speed of an MCS, I would guess, is typically a little slower down there in South Texas. So yeah, up here they tend to be more brief. The wind will last 20 to 30 minutes. I think the events in Indiana, they were a little more closer to 45 minutes to an hour, but still within that time frame where you could use a severe thunderstorm warning. But yeah, for down your way, if it's lasting more than an hour, that kind of gets difficult to handle with a severe. You kind of have to think about a high wind warning in that case.
Yeah, definitely. And like with our most recent example earlier this week, we actually then had another line coming in behind it, which kind of complicates things even further in terms of messaging. But thank you for letting me know that I haven't missed anything out there in the literature.
Yeah, no, there's not much out there yet.
Thank you, Tim, for your thoughts. Jeff, go ahead.
Yeah, just a thought on that question. I wonder in this case, since there was an advancing cold front, whether that synoptically kind of moved the rise fall couplet along and maybe, disturb the overall environment as opposed to having that pattern settle in a weaker synoptic environment that you might see down in Texas more often.
Yeah, absolutely. Yeah, there was fairly strong synoptic forcing just upstream that for sure helped to move this along.
I was also just going to add, based on the soundings you showed, there really wasn't a lot of elevated instability, right? So you had these pressure perturbations that were occurring in, like you said, the stratiform rain region. And these sorts of cases are extremely borderline, like you mentioned, John, and trying to identify the right warning criteria for that is challenging. But from a big picture perspective, one thing that this is helpful for is just to see the signal and see what tools were best utilized in this situation, which you both really showed very well.
Yeah, it's the one of the big challenges in this is being able to recognize what's going on, right? You start to get these wind gusts and you need to be able to recognize the dynamics that are behind what's producing them first, and then figure out what warning type to issue if you need a warning.
Absolutely. Are there any other questions for Tom or John? Okay, if not, again, I should have said this at the beginning, but this presentation was recorded, so we'll have it up on our Eastern Region Science Sharing website, Google site section by later today. Again, John, Tom, thank you so much for your presentations. Really well done, really well organized, and really good things to think about moving forward for both conceptual model, right? Thinking going into these forecast situations, albeit uncommon, right? Like you mentioned in your talk, but still nonetheless something we need to be considered, and the tools involved.